Okay, now that we're all caffeinated and re-energized, it's time for the question session of these really nice talks. So ask all your hardest questions to our speakers. John.
Yeah, I have one follow-up to Neil's question that I'm out of from the during on the analytic continuation.
Yes.
So when you do alpha the minus alpha, factor by there, how do you know that you're getting e to the IS versus e to the minus alpha?
I do the computation. I do the rotation.
So you're not just doing alpha to minus alpha, you're doing something else.
I'm rotating it through the lower half complex plane. That is the prescription.
That's more than just doing alpha.
Are there poles? Are there branch cuts in alpha?
They're square root expressions. Yeah, so that's the way to do it.
You must be picking some particular path in the complex plane.
In the lower half complex plane.
In the lower half.
Yes, any path. There's no fine tuning.
Is it about sine of alpha, of sin of alpha,
and square roots?
And you get exactly minus.
But they have to have square roots.
Yeah. There's only branch cuts.
The expressions involve square roots. I mean, even the red expression in terms of the area involves square roots of the lengths squared. I mean, when you look at the expressions for for different lengths, they involve
Yeah.
So there's one branch cut at alpha minus alpha being negative, but that is resolved by saying you go to the lower half.
That's right. So that's the only kind of ambiguity.
So there you get minus I or plus I, but that's kind of defined by going through the lower half.
So the choice to go to plus I versus minus I is choosing no effect.
Yeah.
Well,
what's the motivation?
To get the correct Euclidean action.
Yeah. Yeah, you see,
and look, of course, if this is not a truncation of anything, so it really applies to all degrees of freedom in that path integral.
yeah. So, but this is not a good explanation. But if you want,
it is an analytic continuation. Analytic continuation is just a mathematical device to compute something that you cannot, compute in one regime but in another.
You could say that, but there are different analytic continuations possible.
There is none known in full quantum gravity for the path integral.
But look, I mean, you can calculate, you can just use the radical calculus. You can calculate it in the Lorentzian and you can calculate it in the Euclidean. So you know these two results. And then you can see that you get from one to the other in the lower complex alpha plane by new continuation. That's all. And that's our first motivation for saying that.
I think the motivation should be stronger than that, because I think there is a point of view that the Lorentzian path integral is the right one. Okay, and the Lorentzian path integral is a very oscillatory integral, so very hard to calculate. But there's this approach called Picard-Lefschetz theory, which goes directly from oscillatory Lorentzian integrals, that type. It goes from oscillatory integrals to the correct set of saddle points and steepest descent contours. Okay, and it's unique. So
saddle points,
people,
we're doing full quantum gravity. So I think we're just talking about two different stories.
No, we're not.
Yes, we are.
Okay, so I actually have some notes prepared about, I think people haven't absorbed this point, that let's not do 4D gravity. Let's do
no. We're doing 4D gravity. That's the whole point. And I'm just saying the only analytic continuation that's known for the full four-dimensional path integral, no cosmological truncation, is the one we're using. If you come up for full 4D quantum gravity with an alternative prescription,
that's what I'm advocating,
and compute the same things we have been computing, and if they are different, then we have to decide which one is, the more realistic or better.
Okay. So I'm arguing that in principle, there should be a unique definition of this Lorentzian path integral given by contour information.
this becomes a story that's probably impossible to do in a full quantum field theoretic
Well,
context.
it's only impossible if you don't try. So,
No,
all
just
the
express.
examples I know of, which are much simpler, but
Yeah, but that is
there is a unique.
yeah, but that is a problem to generalize insights and computations one has done in these very, very simplified models, mechanical truncations of a full QFT path integral.
No.
They tend not to generalize.
No, but Renata, let's say the following.
Yes.
Let me do a really trivial problem. Let me take your action, but with two triangles. Okay. So discretized action, you define it Lorentzianly. It's still a hugely oscillatory integral. I claim the answer to that integral should be uniquely determined by Picard-Lefschetz theorem, i.e., you find the appropriate saddles, you find the steepest descent contours. The answer is unique. There's no choice.
But it's you who are putting up the Picard-Lefschetz thing as the one that should be determining what the correct physics is.
No, I can argue why it's correct.
Well, I'm just saying there is no obvious way of translating this to the full path integral, despite trying.
No, you've got a finite dimensional integral.
But I'm talking about the infinite dimension, a two-dimensional, a toy model.
First comment, it's not an integral.
Why is it not an integral?
It's a discrete sum.
It's a discrete sum. Okay.
So even
No, but you're integrating over length.
No, you do not. I mean, I do. Well, anyway, I do sometimes, but it's you're summing over triangulations. It's discrete variables. You sum over different.
Oh, I see. So all the triangles are the same volume.
That's right.
Okay.
Yeah, it's not quantum radio calculus. It's not quantum radio calculus.
So it's an oscillatory sum.
It's an oscillatory sum.
Good.
I have tried to define analytical combinations for sum, which doesn't work. So
I thought you said it did work.
no, it doesn't. For sum. Well, maybe you can. It does not work. I looked at these concepts like discrete analytical combination. It's very different from the from continuum things.
Interesting.
So it does not work.
Yeah.
I found another technique, which is a numerical technique of accelerating the convergence of series,
Right.
which can give you results.
Right.
But also as a further comment,
Interesting.
let me maybe push back on the unique Lorentzian path integral. Actually, you get branch cuts, which sometimes correspond to one of the essential singularities that n equal to 0, but sometimes not. And these branch cuts appear when you have Gleichung irregularities. And so it's not very clear whether you should exclude them, basically, that Renate does, or which side of the branch cut you should include. On which side of the branch cut you should go. So these are on the Lorentzian continuum.
Right. So in principle, the way to define things, which is very physically motivated, is start with the Lorentzian integral or path integral, smooth the function, these oscillatory functions, with a certain class of functions, like a window, which essentially makes it converge on the real contour. Then you have to, so that physically this is what happens when we do quantum mechanics. We never see anything exactly, and so we're always smoothing. Okay, so this is very physical prescription. So now you show that for a certain very large class of smoothing functions, they will vanish at infinity in the complex plane in such a way that if you deform your original contour to some contour where it converges and take the limit, the smoothing function, smoothing length goes to infinity, the two integrals are identical.
Yeah, but
sorry, I should say the arcs at infinity do not contribute.
Yeah, I mean,
so that's a very general, very physically motivated way of defining oscillatory path integrals.
Yeah, no, that is still relying on analytical continuation. What
Absolutely.
I'm saying is that you can have branch cuts on the Lorentzian contour.
Generally, the actions we're interested in don't have branch cuts. So where do the branch cuts come from?
In this formalism of Vecchi, if you do introduce lengths,
I see.
You can do these analytical continuations sometimes, but
No, if the action
volumes
if the action is not
volumes will be
are in
square roots. Yes.
Constellations, there you have also branch cuts.
I see.
Physically, they correspond to constellations where you have less or more than 2 light forms. And they do appear in cosmology and actually physically when you expand too fast. So it's kind of related to, or what the name, a discretization condition which you have in partial differential equations. But the same ambiguity you have in the continuum with regards to the central singularity at n equal to 0 in that case.
Sorry, what's n?
Lax equal to 0.
I was going to talk about the lax because people are, this issue with the lapse is totally resolved by Picard-Lefschetz, and people are quite confused on this point.
Everyone else is confused.
I was, if you would allow me, I would try to unconfuse.
But anyway, so thank you for the clarification, Bianca. But still, of course, it's still the discussion is within a cosmological context. Yeah.
So the matters anyway, it's even a different sum, so it's not very obvious to you cannot use Lefschetz and analytical continuation.
Okay.
If it's a discrete sum, no, you need some other equivalent method, or maybe.
Yeah, I already have a method whose outcomes I've talked about here.
Sure.
So it's not then in that sense directly comparable. But again, also doing this step to the QFT, I think is very non-trivial, right?
At the end of the day, you're going to have to analytically continue back to real time to make any prediction.
Oh, that's fine.
So if you don't understand the original analytic continuation, it's hard to see how you're going to do that.
I understand it perfectly well. Perfectly.
That we don't understand it.
Well, okay, fine. So why do you show any pictures of Euclidean geometries? You should just take your answers, analytically continue back alpha in the lower half plane.
Look,
and plot the Lorentzian geometry.
In principle, we could do that.
No, if I just confine myself to the cosmological sector, that was the de Sitter solution. I can easily do it. However, of course, I'm interested mainly also in all the other, modes of the geometry.
But you could do
And
that
there
with
is,
all of them. I don't see why you can't.
yeah, because you do not have an explicit analytical control of these things.
But you have to solve this problem of going back if you're,
Yes,
if you're going to make predictions in real time.
but this is a problem that is not unique to gravity.
I'm not criticizing.
No,
I'm just saying
you-
this is a problem.
you
that
are,
needs
but
to be
I'm just-
acknowledged.
Definitely, it has already been acknowledged in an answer to a previous question of yours.
But you are asking, for instance, you can answer certain questions in the Euclidean sector, like in lattice gate series. And,
True.
and you never
Equilibrium properties.
No, you can.
The spectrum. The spectrum.
So
Those are equilibrium properties.
I don't know what you call this is just
Static.
vacuum value.
Yeah.
But they are nevertheless, I mean, in quantum field theory, all we calculate are time-ordered vacuum correlation functions. And these are the ones who calculate in the Euclidean sector. You never ask people to, I want to see this field configuration in the Gaussian space.
That's not what I'm saying. I'm saying you want to calculate dynamical properties in real time.
Well, I mean, the Euclidean setup can address certain questions easily, other questions less easily. And correlation function in real time is exactly one of the things they cannot address very easily.
Correct.
In
Yeah.
field theory.
Yeah,
So-
but then you have to reconstruct.
One should try.
And you're complaining that we cannot either. And
I'm not complaining. I'm not
Yeah,
complaining.
yeah.
I'm
So
saying it is
anything that
it
has
is
an
a-
explicit time dependence has a non-trivial issue about how do you rotate it back to Lorentzian signature. So
Absolutely, I agree. So that
Yeah.
I'm just saying that
Yeah.
is an interesting problem people should work on. That's
Well,
all I'm saying.
But it's a problem that appears in many places where, including, let's say, many places in string theory, where certain computations you can only do in Euclidean signature.
Totally agree.
So, but here, this problem poses itself. So I presented some observables like dimensionality, where we are working on the assumptions that doesn't actually depend on the signature of the metric.
Mhm.
So if you find this in our rotated framework. That probably means the same is true there. Then we have the scale factor behavior and the fluctuations around that, which already covers kind of cosmological things, where we see that there is our a priori, time variable, which hasn't a physical interpretation. Apparently on large scales, we can interpret this as a cosmological proper time, and then we fit these perfectly, beautifully on a proper time description of de Sitter, and we rotate it back. And as you're saying, then the cosine will become a cos. So that's a very natural interpretation. If you give me arbitrary, time-dependent observables, yes, I will have a hard time. But it doesn't mean that the rest is worthless. But there are clearly there are computational difficulties in computing the full path integral. So we're using this mathematical trick, and then obviously we have to rotate back. We are not sweeping under the carpet. That is difficult. And once you start coupling matter, it becomes even more tricky. But in a way, it's a well-defined problem, right? Certain thing, kind of what Euclidean experiment do I have to perform, and what does it tell me about Lorentzian properties? And of course, if you're talking about thermodynamics, which we are addressing with other types of path integrals, also there the question is, how does a certain property of these Euclidean path integrals, which are a priori are totally unphysical, you're making mathematically motivated choices, what do they correspond to in terms of the real physics on the Lorentzian side? So that's already a baby version of these difficulties.
Okay.
Yeah. So that's in a way not too different for the full path integral.
So,
Is there a follow-up or new question? Are there first any follow-ups here? Okay, go ahead.
Question for Neil, in your very interesting talk. You were initially advocating this sort of minimalist viewpoint.
Yes.
But then towards the end, you kind of casually snuck in the fact
36 fields. Oh.
That, well, the Higgs has to be composite. Now, there is as you know, a huge body of literature about composite Higgs.
Yep.
Often that involves, new fermions, new gauge fields,
Yep.
all kinds of extra stuff, and typically is very complicated and somewhat problematic.
Yes.
So all of a sudden, with that little version of that comment,
Yes.
I think the whole minimal perspective
Disappears. Yes. Super. Okay. So to be fair, I started my talk with Higgs inflation. So I'm also appreciative of the minimality of the standard model Higgs viewed as a fundamental field. Okay. But no, we were forced to say the Higgs field is not fundamental by this anomaly cancellation. It wasn't a choice. But wait.
Composite Higgs, you've got a much more complicated challenge.
Well,
More fermions.
no, absolutely. Absolutely. So the only hope, and it's only a hope, is that these dimension zero fields somehow conspire to make a composite Higgs. Now, yes. So why is that even conceivable? Okay. There are two reasons. One of which is that phi is a dimension zero field, right? So you can exponentiate it. It's the analog of the string worldsheet coordinates in 2D. You can make vertex operators out of phi, and we know that string theory dimensions, string theory worldsheet coordinates can be used to generate operators of non-zero dimension, which are vertex operators. So that is very appealing, is that somehow I would exponentiate this phi. I certainly can see in free field theory that I get power law correlators, looks something like a massless dimension one field, which may be, the first approximation to a Higgs field. Okay, so that's the dream. The other reason which makes me, but it's only a dream, okay? The other thing that I'm very interested in is a recent proposal by Ramachki. I don't know if you've heard of this. So he's a lattice gauge theorist and nuclear physicist who's expert at large N. And he's pointed out something very interesting. Actually, it's reviving very old ideas. So if you take lambda phi to the fourth theory at negative coupling, where it looks crazy, it would see it is asymptotically free, okay, at negative coupling. But you say classically it's completely unstable, so why do I care? There is a very old analysis of the large N version of lambda phi to the fourth in the 70s, first done by Coleman, who got the wrong vacuum and claimed there was a tachyon at large N, and then improved by Abbott. And what they found is that there is a vacuum which spontaneously generates a mass, and it essentially uses this running coupling. And so that would be a very nice solution of the hierarchy problem, is that basically you say there's some large N theory at high energy. The coupling is very small at high energy. It's asymptotically free. As I run the coupling down, the coupling becomes large. And again, you hope to get something like a Higgs at a scale exponentially smaller than the Planck scale, let's say. So that's a very interesting proposal. He's recently extended this to the abelian Higgs model coupled to these ON. So it's only abelian gauge theory. He claims you do get a mass for the gauge bosons. So this is very recent work. It's just in May. Now, why should lambda phi to the fourth have anything to do with dimension zero fields? You can do a very strange field transformation to rewrite lambda phi to the fourth theory in terms of dimension zero fields. And if we have time, I can show you. So again, you basically say that the dimension one field is the exponential of the dimension zero field. You can change variables, and this box phi squared theory becomes lambda phi to the fourth at negative coupling. So I'm hoping for a whole set of coincidences. They may totally fail, but yeah, that's the hope.
Is there a follow-up? Bo, did you have follow-up? You had. Otherwise, we continue. Okay, but I think you had your hand raised for a new topic.
Yeah, that's right. Okay, so that's not the follow-up. This spectral dimension, two branch does that have any relevance to the larger scales? Do we learn anything about space-time at larger distances from that? I mean, is there a reason that it is not relevant for what we see around us?
Yeah, so there were two arguments. So this spectral dimension is one of the kind of canonical observables that people have used in these systems of random geometry, starting, of course, in 2D. But then, these were these kind of non-critical string theories attempts of, a long time ago, even before I started doing physics. But it's a nice observer because it's diffeomorphism invariant, and you can just characterize the properties of geometry. So in a fractal-like system, what one had seen until CDT came along was always kind of no dependence on the scale of this spectral dimension, although the spectral dimension would be simply, in principle, a non-integer, right? So it's this diffusion process. So in four-dimensional Euclidean dynamical triangulations, the spectral and the Hausdorff dimension were used also as observables, and there everyone thought, well, obviously it will be four, because if I use four-dimensional building blocks, I mean, what can emerge? Anything that's not four-dimensional. But simply that turns out not to be the case. So there one finds two different phases characterized by, say, Hausdorff dimensions, spectral dimensions that have nothing to do with four-dimensional manifolds, but in one case are related to branch polymers. So, and very interestingly, it is a very generic, it doesn't depend on details at all. It doesn't even depend on the dimension of the building blocks. So you did EDT models with 5-dimensional building blocks and 3-dimensional building blocks and 4-dimensional. They all become branch polymers in the continuum limit. So it's a very robust thing. But so you see already, it's as an observer, you would say, well, the dimension, that's totally uninteresting, right? Because that's something that's fixed. If you go non-perturbative, it turns out to become dynamical in certain ways. So what happens when you measure the spectral dimension in CDT? Well, I didn't show you a curve, but in the region where we can measure, it's an increasing curve from very small scales, where, you know, we can extrapolate with really big error bars to something that might be 2, plausibly, to something that asymptotes plausibly to 4. So there we say, okay, wonderful, classical limit 4, but there is a genuine quantum effect at small distances, which, so that's...
You have some indication that it's not just staying at...
No, it's not a plateau. So it's, you know, continuously going to, which of course tells you that this is not a classical manifold in any way.
Do you hope that this will explain the area law?
Well, no, this is, well, this dimensionality is a very coarse way, you know. So of course, unless you put in more details about what kind of geometry this is more locally, well, it doesn't tell you very much. I mean, you know, even if it comes out as 4, of course, it doesn't guarantee you that this is a nice 4D manifold. The 4 could be, you know, your microscopic geometry could just conspire in a certain way to produce a number 4 for totally different reasons, you know, than it being a nice geometry. So one has to be careful. But I would say if it's not 4, then you, in no limit, then you have a problem. Right? So this is how I would argue. Yeah.
Any more points on that? No, okay, so Paulo was first, and then we go.
Thinking about this 2-dimensional 4. But can you get 4 or not?
From what?
I mean, the dimension.
Yeah. It asymptotes to 4.
Asymptotic what variable?
It's the spectral dimension, in the diffusion time, you know, that's what you're monitoring for the spectral dimension. How big is the diffusion cloud as a function of your diffusion time, which is kind of in external time. Yeah. So, and then the leading behavior kind of you know, how does that volume, the volume of the cloud scale as a function of square root sigma gives you the spectral dimension.
So unless you will get 4, is non-physical.
Yeah, but of course, we can measure it not in a region where things are genuinely classical, but we see something that with a, you know, minimal number of parameter fits asymptotes to 4. That's the best we can say. But of course, you know, other people have then run with this idea of the scale-dependent spectral dimension, and, you know, people doing FRG calculations, etc. So one can find such behavior.
Follow up? Or yeah, plus Bay and then yeah.
Also follow up.
Answer to Paulo. So the fact that the household dimension or the spectral dimension is equal to the physical dimension of your space-time, this is not a criterion. I mean, in our beloved 2D world, I mean, the household dimension of typical configuration is 4. But still, it's just viewed in 2D quantum gravity. But it just shows that the ultraviolet fluctuations of these things are very wild. But they are wild in a well-defined way because the household dimension is 4. It is not fluctuating. I mean, a typical configuration, the probability 1, if the volume is very large, it will be 4. But still, it is 2D quantum gravity. Quantum theory. So the exact dimension is not saying that it's unphysical. It is not the dimension that you would like it to be.
Yeah, but there, of course, in full quantum gravity, there is of course aiming for a classical limit, which in Liouville gravity is, debatable.
friendly, that if you restrict this diffusion process just to time slices, then you don't get three at large. You know, there's no
Yeah. Mhm.
asymptoting to
Yes,
three
yes,
dimensions,
yes,
which is
yes.
super interesting because it means that it's truly a space-time result. I mean, you can't, you know, there's no, the picture of this quantum space-time as being foliable by three-dimensional things building up a four-dimensional thing just doesn't, it isn't there in your typical communication. So it's really genuinely, you know, a four-dimensional result. You need the diffusion process to be defined on the whole of the four-dimensional configuration.
Yeah. So yeah. Mhm.
More history.
Yeah. So what you're saying is true, but well, I would rephrase, you know, the interpretation of that. So on a lattice, so if you choose, you know, a fixed time surface, so this is a very singular thing to do, actually in the same way as when you do a quantum field theory, observables, you know, related to whatever, being it one-dimensional lines or subsurfaces, well, they're highly, highly singular things. So you need to smear them out to make them into proper observables. So the same applies here. And actually, what if we allow the diffusion process kind of to wiggle around, you know, it fits again more with the canonical picture. So you don't find these fractal dimensions. There, one could say to some extent an artifact of forcing oneself in a very singular way onto a submanifold. So that's some you shouldn't do. You should be very careful in how you interpret these things.
Somehow the embedding is very wild, but it doesn't necessarily mean that the thing it's in, the thing is the height that's embedded in is particular. Or if you're thickening.
Yeah, we are thickening it a little bit, and that relates really to kind of renormalization. That also just says, well, and it fits with standard QFT logic. You know, think of Wilson lines. They're of course very, very singular things, you know, to work with. So you have to regularize and normalize them. Yeah.
Any more follow-ups? Then we had it first out.
I have a really simple question. So, you said that there of course no dynamical matrix in the formulation, but it seemed that the triangulation was constructed was resting with some kind of null cone. So what is the understanding there?
So I didn't catch the first part of the sentence, what you said about dynamical.
There is no dynamical matrix in your formulation.
It's a metric.
It's a space-time metric that is dynamics.
You started in the beginning.
Mhm.
You have there's a kind of connection. There is no G mu. There is no G mu.
Oh, there's no G mu. Yeah, okay, yes.
You just-
Well, there is no tensor calculus, so I'm using this wedge idea, you know, giving you the edge lengths.
So it seemed that the triangulation was constructed with some kind of a null cone. So how to understand that? I mean, that one can define a null cone without reference to a matrix?
Yeah, I mean, the building blocks, I flashed it on one of the transparency, like a four-dimensional building block is by definition is flat on the inside. So you think of it, you know, I hand you flat Minkowski space and you just cut out this simplicial object, you know, this higher dimensional analog of a triangle. So it inherits from the Minkowski space, you know, yeah, exactly. So on each inside, it has the metric properties of Minkowski space. So if I wanted to, I could reintroduce a little coordinate system on this block. It would defy the purpose of what I'm doing, but I could.
But you can trace a light rays through the entire triangulation.
You could, if you would think that again, as you know, a single light ray is again a singular
Some kind of Minkowski matrix.
Yes.
Yeah.
Ground with
Yeah.
Not all only on each building block.
Yeah,
So
and
there's
it's
no
not global.
global.
No. So it sits. So the curvature in these triangulations sits at sub simplices of dimension d-2 in a singular manner. So these are not nice. You can think of them as having G mu nus, but the G mu nu will be singular. So they don't sit in any space of smooth G mu nus, but they're sitting full. Yeah, they're full of curvature singularities actually. Yeah.
Simplex and there's singularities at the interface.
Yes.
But then the gluing has to be done in such a way that you do get a consistent global.
Yeah, so it's done in such a way that if you cross from one to a neighboring building, kind of the light cones, they don't they kind of align in a way, yeah. Roughly speaking, yes.
Okay, any follow-up on that? Otherwise, we move on to Sran. Oh yeah, sorry, you were first. Sorry.
I will change.
Sure.
Because I wanted to ask Neil, because I got confused a little bit with your statement about this zero-dimensional fields. Yeah, you present a Lagrangian which contains higher derivatives.
Yes.
Then you are claiming that it's okay. But you claim that there are negative norm states.
Yes.
But it's okay. They can be somehow removed.
Yes.
Actually, I'm not sure I understand how they can be removed, especially if you will have interaction. But even if you can remove it, which will be very interesting to see. I remember it was a paper by Zetkin,
Yes.
where he simply computed the amplitude for such a field exactly with what derivatives.
Yes.
So that it's not unitary. Since amplitude is gauge invariant, what do you mean you can remove?
Okay, good question. So I was just talking about the free theory when I said you can remove the negative norm states. Okay, the interactions is a no. We want an interacting theory. There's been a lot of interesting recent progress on the interacting theory. We're working actively on it, but the most interesting recent paper was by Holdham, I think in February this year. So what he does, so his claim, I'm just repeating what he told me, is that Zeitlin's calculation's incorrect. That Holdham has rather carefully plotted the, well, he computed the running of the couplings. There are two, if you write down the most general renormalizable theory, which is shift symmetric in this field, phi goes to phi plus constant, and involves four derivatives. It turns out they're two dimensionless couplings. He's calculated those and shown that the theory is asymptotically free. Then he calculates cross sections, and he shows that in one region of parameter space, all of these are positive. There's no problem with negative norm states. And yes, so I asked him, how is this compatible with Zeitlin? And he said, oh, Zeitlin just made a mistake. I haven't asked Zeitlin, I have to emphasize. So, yes. Surprising. Well, read Holdham's paper, and he clearly says this interacting theory is well defined, as far as he can tell, in this part of parameter space. So there's part of parameter space where you get negative cross-sections, part where you get positive cross-sections, and very, very interesting phenomena that these cross-sections do not scale with energy in such a way as to violate the unitarity bound. They scale with much lower powers. And so in part of parameter space, for example, there's a special line where the cross-section goes like 1 over s squared. Whereas naively, you saying these high derivative interactions would give you positive powers of s in the interaction. So he actually finds the opposite. And the way it happens is very interesting, is that the negative norm states actually are responsible for canceling the bad high energy behavior in just such a way as to leave you with a positive cross-section. So this is a very active area of research, and I think it's really interesting.
because
Do you need a microphone?
no, I think it's
Okay.
because in the paper by Arkady Tsapin, it was only one coupling which was considered, and Bob Holden's paper, as I understand, they very much rely on some very precise relation between the 3 points of vertex. Only there is some extra.
Okay, so can I draw a picture? Yeah. Oh, there's better.
Yeah, maybe.
Yeah. Okay. So, so the most general theory is integral renormalizable. Is this one plus lambda 3 d phi squared box phi plus lambda 4 d phi squared all squared. So Holden discusses this theory for arbitrary lambda 3 and lambda 4. And then what he shows is in this diagram, lambda 4, lambda 3, there is a special curve. And this, inside this curve, on the left of this curve, you get negative cross sections, except on this special line, lambda 3 equals 0, where the cross sections are also positive. To the right of this curve, everything is fine. Now, Zeitlin calculated precisely on that line. On that line, Holden says everything is fine. And that's the contradiction.
Well, I don't see how it can be compensated because you have 4 point vertex only compensated, and you don't have anything coming from the.
He gets cross sections going like 1 over s.
There is a square. Number, there will be a square part, which is the 3 level up. I don't see how it can be cancelled.
It cancels precisely because of the negative norm states. Yeah. So the way Holden does the calculation is quite tricky. Basically, he introduces a mass into this theory because it's very infrared, this theory. So he introduces a mass, calculates at finite mass, and then takes the massless limit by differentiating the answer and using L'Hopital's rule. And you have to differentiate the answer for your cross-section several times, like 2 or 3 times to get the answer. So, and it's that differentiation which ends up producing this negative power of the S. It is not clear. So we're actually trying to repeat his calculations, but with no mass. Yeah, so I was very interested in Anselmi's approach because, in fact, I think this is perfect application of that approach, that one would like these fields to be fakions. All this problem with negative norm states, etc., would be removed if one could just say there are no external states for this theory. So there's just the vacuum. That would be the dream scenario, is that this field only has a vacuum. Even in the interacting pictures. There are also very funny things that happen on this line. So these 2 couplings, there's a special, this line is precisely where this action becomes a perfect square. So when it's box phi plus lambda 3 d phi squared all squared, that's when lambda 4 is, I've got a minus sign somewhere. It's actually lambda 4 is minus lambda 3 squared over 2. And as you approach this line, they're very, very special behavior on that line where the action is a perfect square. So that's particularly interesting limit. Yeah, so exactly. So this is what happens. You have this cubic coupling. So say you do a 4-point amplitude. You have this, and you have this, and you have this, and you add them all up, and they cancel exactly. Okay. So tree level diagrams all cancel on that line.
Well, in principle, this type of extra box can be written as an exponent of some entire functional box in non-local setting, and if one can do everything.
Mm-hmm. Yes, absolutely. I mean, I think another method other than Holdham's would be very interesting. See if it gives the same answers.
There's a follow-up from.
Sorry? No. Oh, I don't know. Maybe. Yeah, maybe. Haven't thought about that.
Follow-up by Luca.
Just a comment on what Neil said. That is in your case. I'm not completely sure that you can really use this result to justify your absence of like possible instabilities due to this because in this case, I think the full theory really has a master, which will give a propagator.
He always takes the masses limit.
Yes, but you see, in the end, what really grows, the cross section really goes like 1 over s. Which would be increasing is the total inclusive cross section. So
yes.
Take the single amplitude for instance, because what it does basically it writes the Lagrangian in terms of like a massless two derivative and a two derivative cost massive thing. And you can do that if you have a mass, of course. And then he says, okay, let's compute the cross section for this field and at high energy, when the mass of the small particle is then you see in that case that there is a cancellation between when you sum basically different cross section. You consider the total inclusive cross section.
No, he does the differential cross section.
Yes, but inclusive one. So if you take just the cross section, you do, for instance,
There's only one candidate particle, so what?
Mass, there is split between a massless and a massive derivative. This is very important. But in your case, we really start with no mass terms, so you have a full derivatives field with no mass. So I'm not sure that
Only what, if you write it this way, only one of the fields is not a ghost. One is a ghost and one is not a ghost. So he computes a differential cross section for the non-ghost.
It's the sum of cross section due to the non-ghost and the ghost.
No external particles are ghosts.
Otherwise, you do the cancellation.
The cancellation the mixed state, the external state in the ghost and the non-ghost.
Otherwise, the single cross section will always go, just because it's type of interaction. It's really the total inclusive cross section that has this cancellation because of the negative and plus signs. And you really need to start with a different Lagrangian. You cannot just start with the box square without master. In this sense, I would say, in your case, it's true that in the flat, in the standard free case, we can use basically the Loll argument, which says that you have some K variant with everything. But we didn't show the full, let's say, data for operator, which has basically box square plus all contribution, like all the interaction contribution.
No, those are not, the interactions don't come there. The interactions come in these terms.
Your action for the star field,
yeah,
only show the box square.
Yeah, that.
Also the avenue.
Sure. So yeah. True. In a curved background, in a general curved background, that's, yeah, we need this to work. That's true. By the way, it does work in a conformally flat or even in a Ricci, in a Einstein background. It does work, but not in a general background. Yeah. Absolutely. No, everything is still open.
Please.
Continuing on this topic of your anomaly cancellation.
Yes.
An analogy with anomaly cancellation in gauge theories.
Okay.
So if you have let's say, an odd number of massless fermions coupled to a gauge field in some anomalous representation, then you will have a gauge anomaly.
Right.
And you can cancel that gauge anomaly by introducing some scalar fields with a Vesumino term.
Mm-hmm.
However, so this is very similar to what you're doing here, because you have an anomaly coming from some matter, and you cancel it by introducing scalar with a particular disregard. But this model with cancellation where you have scalars is typically just regarded as well, it is a non-normalizable theory because it's a nonlinear sigma model with some particular function. Now, I don't know if you care very much about renormalizability, and I don't know if
it's good to have.
arises in this particular instance.
As far as I know, this is perfectly renormalizable, and even if I put it in a curved background, it's renormalizable. So, yeah. Yeah, and these couplings lambda 3 and lambda 4 are asymptotically free. So it looks like a good renormalizable theory.
More follow-ups on that? Yes.
So you mentioned very briefly at some point some connection to asymptotic safety. So can you say what is the current status of that? And in particular, you know, at some point John was asking what is the success for a theory like quadratic gravity or asymptotic safety? How do we know that it's good? And what can we learn in that direction from your calculation?
Yeah, okay. So let me make a general comment. So that referred to work by Jan. So I would defer that question to him. You know, the struggle to establish some kind of connection between asymptotic safety scenario in a simple setting, but he should comment on this. So I would say my general comment is that we are just maybe scratching the surface of what renormalization really means in this non-perturbative, you know, geometry is dynamic or context. And maybe currently our imagination is a little too limited, but it's good looking at scenarios where we think we have some understanding. And so maybe Jan wants to comment on this recent to be published paper.
Yeah, we talked in a couple of weeks. So what the thing we are doing is just that we are taking the simplest model of asymptotic safety. I mean, the Reuter model, the very simplest model with Einstein action. And we are taking it literally, you know, that you have a running coupling constant of G, gravitational coupling constant, and a coupling constant. And then treating this as a standard effective action. So we have a de Sitter space there. And the radius of this de Sitter space is now a function of the scale factor K. And we simply match that to our computer simulations. And then we see whether there is a correspondence between the running of there and whether we are led to ultraviolet fixed point. And as you can imagine, well, it's a little bit tricky, like it is in the asymptotic safety calculations. It's an approximation, but nevertheless, I would say the probability 0.8, we see an ultraviolet fixed point, and moreover, we see the infrared limits very nicely. I mean, so what we see is the Gaussian fixed point, and we see also this fixed point of and Wang, because they are studying a model where they have a foliation actually, and they find that infrared fixed point there, and we see that it scales in the same way. Well, the product of G and lambda, which is dimension, it scales in the same way in these two fixed points, the infrared and the Gaussian. And we see this scale. This just comes out of the computer simulation. So this is the first times that we managed to connect concretely to asymptotic safety, and I think that's very nice. But still, it's numerical simulation, and we are not entirely sure that this is right. I mean, there are some error bars, and as you know, this is how it is.
Yeah, this is using causal dynamical triangulation.
Yeah, it is. Yeah.
Not his, because Roberto described one calculation where there's a truncation in the number of modes. But you're not using that.
No. It's not. We're using kind of number
Truncation is the Einstein-Hilbert action.
So the first calculation of Walter, that was just to keep these terms, forget about everything else, and then study the running of the coupling constants, and then what he saw was an ultraviolet fixed point, which of course was a little bit surprising. So I would say that what is nice about the lattice simulation is that it is also an approximation, but it's a completely different kind of approximation. And the fact that if you in both cases see such an ultraviolet fixed point, well, maybe it gives additional weight to the existence of this fixed point. So that is the status, but in a couple of weeks, it will be on the archive. Yeah.
But maybe the original connection came from the similarity in the spectral dimension. Safety.
Yeah, but yeah,
that it also goes to two.
But it is true. But I would like to make a remark there. I would say so. It is true that after we observed this, as another reported, the spectral dimension of 2 in the short distance, then it's a little bit like black hole entropy. If you know the result, then any approach needs to be able to
without revealing. That's right. Yes.
How much weight that has. Okay, that's good.
Yeah, but in the asymptotic safety, it's just canonical dimension.
Yeah, I'm sure.
Yeah, but I think the interesting thing would be really reproducing evidence for the UV fixed point, with a totally different method.
Yeah.
Follow up?
Yes. I was a bit confused about this whole discussion, also on some point on a slide there about this. It seems to me that, of course, the methods of dynamical triangulations and function harmonization, for example, are different, clearly. But I thought the physical scenario being investigated was the same, namely looking for UV coefficient as a critical point.
Well, in a very grand, I agree. So in a very grand scheme of things, yeah, we are doing both, quantum field, we are really believing in the principles of quantum field theory without fancy, anythings. But nevertheless, I would say computationally, we're genuinely complementary. I mean, in the anything analytically, including FRG, of course, makes lots of assumptions. I mean, you're pushing this continuum description, to a region where you're entirely unsure, how far it's really valid,
Physical scenario, like, is it reasonable to call this a method to investigate the asymptotic safety scenario?
Well,
say that.
Well, as Jan just explained, it is an independent way of finding evidence, but it's genuinely independent because we have the full degrees of freedom there. So we are not truncating the action in that way. Yeah.
Sorry about. I mean, they're both functional representation and this lattice approach. I mean, what they tap into is just the Wilsonian way of
that's what I was.
Yeah, it's just different realizations of this.
That's what I was saying, but then I got confused by a comment in a slide where at some point you mentioned this, and in the same sentence you said something like it's an effective theory.
Yeah, so effective. I meant this in a totally different way from the standard effective. I meant effective, we are using our formulation and the observables I discussed. We are measuring them in the vicinity of the Planck scale. So on a, between 10 and 20 Planck lengths, that's what our universes are like. So what we are saying is, to answers of, what is the UV completion? Is it an asymptotic phase? Is it in principle compatible with other things? So what I wanted to say is in principle also compatible with other things, but at the Planck length, it seems a very nice, effective description, of whatever quantum physics happens there. But what happens at Transplanckian energies, maybe totally other things will happen. We cannot look there with our methodology.
So not effective in the sense of EFT below.
Well, yeah, that's right. No, it's effective at the Planck. At the Planck. It's a somewhat it's a slightly unusual, way of phrasing it. But I had so little time. I would have said it. Yes, yeah.
I mean, a possible outcome of such an investigation, it would be that because we want to take a limit where A is that the cutoff goes to 0. But of course, we have to match it with your observables if you claim are staying fixed and so on. So a possible outcome would be that you cannot take A to 0. I mean, you cannot take the cutoff to 0. And that would be an indication that there is no automatic fixed point. Right. I mean, so it's a strong message in the sense that it allows you to address this question. Does this automatic fixed point exist or does it not exist? Sure. And we had a chance of answering it. And well, as I said, when I mentioned these 80%, it turns out that our data right now, they favor slightly the existence of automatic fixed point. But it is in a border region where, I mean, if you could, I would really love to make the systems a factor 10 larger. But we cannot do it.
Thank you.
Well, but again, of course, what is 1/10 of a Planck length compared to a Planck length? You don't know.
If you trend in how A is scaling, is it going to a constant or is it going to 0?
Yes, follow up just regarding your coming work. So exactly how are you relating our lambda k gk with the CDT parameters? So because I remember I discussed this extensively with Giuseppe Clemente, who was in Nijmegen at some point, and we were really struggling relating the two axes of the CDT with the rounding capital.
They can be related very neatly, I would say. Now, but I think we cannot. It will require me to go to the blackboard and give a seminar, but I will be happy to go in detail with you. So we have understood how to do that now, and so that maybe the way I will tell you is maybe not the way you would like to hear it, but we can relate them now. We can understand how to do this.
Although the functional one is completely Euclidean.
I'm sorry?
The functional normalization group is completely Euclidean.
Yeah. Yes.
Yours is
yes.
not.
That's right. That's right.
Yours is not. But nevertheless, you say you can relate them.
Yeah.
There is some where there is more reason for the transversal calculation in Lorentz, but of course it's more complicated, and there is only really
So our result in the infrared matched to these fully aided calculation of Planck.
But in that they don't find big differences, right, between the Lorentzian or not. No, they don't find. Yeah, okay. Whether I believe that is a different question, right? That's, yes, we do. Yes, we do.
Yeah, but again, I cannot go into it. Actually, our work might need a revival of ordinary Euclidean dynamical calculations, because we have understood now how to discuss the and it's different from what you naively would expect. So, but again, this is a longer discussion. I'll be happy to tell you.
This has been a very long and intense discussion. This very briefly.
Very brief, it's observational question, very brief and short. So I have a question and a challenge to you, Nick. So question is basically, well, you predict the scale there in power spectrum, but there is a running of NS, which is very crucial and it will be measured more precisely.
Yes.
Do you have a precise prediction for that?
0.
0.
Yes.
Okay, then that will distinguish.
Yes. Absolutely. Yes.
When you get particularly because the running is what generally multi-field equation predicts.
That's right.
And okay, that's correct.
That's right. Yeah.
And the challenge.
It is, just to elaborate, it's a critical exponent. That means it's essentially dimensional analysis. Dimensional analysis gives you a scaling, and you don't get a running of the index. So our setup predicts 0 running.
That goes not the tensor to scalar, it's the running of index.
Yes.
Okay, that's what.
Should be 0. Absolutely.
Okay. Okay. Then the second question is, well, you do explain the, for example, you have right-handed neutrinos, and the mass of the right-handed neutrinos is about 10 power of 8 GeV.
Correct.
But in that, I assume you take it as a dark matter kind of.
Yes.
Well, in dark matter, there is a big challenge for the cerium. This is the cusp core problem. The standard dark matter cannot address it at all, and
this is a big controversy. My take on it is probably the resolution is CDM is fine. Yeah.
Okay, with that, let us thank our 2 speakers again. Yeah, please don't run away for lunch.